Hey everyone, so today we are going to see about the sampling distribution for S square. Earlier we have seen the sampling distribution for X bar, right? And there we had a very nice theorem called as a central limit theorem. What does the central limit theorem says? It tells you the distribution for X bar, okay? Irrespective, whatever the distribution your X is having, we know that X bar do follow the normal distribution with mean and variance to be this. So that's the plus point of central limit theorem, that we know the distribution for X bar, it is normally distributed. But we do not have such a nice theorem for S square. We do not know what is the distribution for S square, what distribution S square follows. It can be anything. Okay, so again let's just recall some of the things. So what was our scenario? We have a random variable X. We take a sample of size n, x1, x2, x3 up to xn. Okay, so you take a first sample of size n, you take a second sample of size n, you take a third sample of size n, and so on. Then you find the mean of each of the sample, mean of the first sample, mean of the second sample, mean of the third sample, and so on. And then you can find the variance, variance of the first sample, variance of the second sample, variance of the third sample, and so on. So we denote by, say, small s1 square, this is small x1 bar, small x2 bar, small s2 square. This we call as a statistic, this we call as a statistic. It's the output of all the possible sample sizes, all the possible samples of size n. Okay, and the probability distribution of the statistic is called as a sampling distribution. So we know this is always normally distributed thanks to central limit theorem, but we don't know the distribution for S square. Again, recall once again how do we define S square? It is the variance, right? So if you have a sample of size n, so instead of dividing by n, we divide by n minus 1. We will see the reason in estimation theory. Summation of xi minus x bar the whole square, right? I minus 1, I from 1 to n. So this minus this the whole square, plus this minus this the whole square, plus this minus this the whole square, divided by n minus 1. Then you get your small s1 square. To find small s2 square, the second sample, first term minus x2 bar square, this minus this 2 square, this minus this 2 the whole square, divided by n minus 1, you get s2 square. So this is the formula for S square. Okay, so now if we don't know the sampling distribution for S square, then how to solve that problem? Well, what people observed was, when you simplify this S square definition, what people observed was, when you multiply it by a nice number, and that nice number is n minus 1 upon sigma square. What you do, you have all s1 square, s2 square, so on. You multiply all of them by n minus 1 divided by sigma square. You do that. You get new set of values. Then if you find the probability distribution of that, then it says it follows chi-square distribution with n minus 1 degree of freedom. And that's where chi-square distribution will help you. We have talked conceptually what is chi-square distribution, but here we are actually going to use the table. So now let us try to understand why n minus 1 into s square upon sigma square follows chi-square distribution with n minus 1 degrees of freedom. Okay. Now what is summation of xi minus mu the whole square? So I am considering with this summation. Okay. Now what I am doing, I am adding plus x bar and minus x bar to this. Now we call this as your a and call this as your b. So what is a plus b the whole square? A square plus b square plus 2ab, and then you take the summation inside. Okay. Now this I have written as it is. See, this is independent of I is running from 1 to n. Here there is no I term here and here, so you can take out this term outside. What is summation 1? I is going from 1 to n, it is n. So this comes outside, summation of 1 is n. So this is the term. 2x bar minus mu. Now what is this term? This term is always 0. See, if you have a data set, say 2, 4, 6, 8, you find the mean is nothing but say 5. And if you subtract each term from the mean, and if you add them, your answer will always be 0. So like 2 minus 5 is minus 2 minus 5 is minus 3, minus 1, 1 and 3. So minus 3, minus 1, 1, 3. If you add, answer is 0. So when you subtract each term from its mean and you add up, your answer is always 0. So this term is 0. Okay. Now what I am doing, now I am dividing both the side by sigma square. So when I divide by sigma square, this upon sigma square, but what is this? My s square is what? My s square is 1 upon n minus 1 into this. So what is this summation? It is n minus 1 into sigma square. So this term is nothing but this, and I am dividing by sigma square both side, and x bar minus mu whole square sigma square, and this n I am taking down. So that's the adjustment I have done. But what is the left hand side? If you observe, see my x size, my x, so at the start I should have said my x is a normal random variable. Since x is normal random variable, all my x size are normal random variables. So since x size are normal random variables, when I do this transformation x minus mu upon sigma, what I get is a standard normal random variable, and it is a square, so zi square. So I am having summation of zi square. And if you recall our lecture on chi-square distribution, we know that what is chi-square distribution? A random variable x is said to follow chi-square distribution if your x is nothing but the sum of the squares of the standard normal random variables. And each z1, z2, z3, each is having only one independent variable. Like z1 is depending only on x1. These two are constant, mu and sigma. My z2 is depending only on x2. So each zi is having one independent variable. That means one degree of freedom. Therefore, summation of zi squares will have n degrees of freedom. 1 plus 1 plus 1, how many times? N times. So this is a chi-square distribution with n degrees of freedom. So therefore, since left hand side is a chi-square distribution, therefore my right hand side is also a chi-square distribution with n degrees of freedom. But again, what is this? Since x is normal, my x bar is also normal. Therefore, this is nothing but my z square, right? X bar minus mu upon sigma by root n whole square. So thanks to central limit theorem, I know that this is nothing but my z. So this is again z square. Since z is standard normal random variable, I am taking a square. Therefore, this will follow chi-square distribution. What will be the degree of freedom? It will be 1 because it is only depending on x bar. Rests are constant. Okay. So my z square is a chi-square distribution with 1 degree of freedom. So the right hand side, this is a chi-square distribution with 1 degree of freedom. Total is a chi-square distribution with n degrees of freedom. Therefore, this is a chi-square distribution with n minus 1 degree of freedom. Okay. So that's why n minus 1 s square upon sigma square is a chi-square distribution with n minus 1 degree of freedom. So I hope the proof is clear. Now let's take some examples. Okay, so now let's go for the first example. So what is the first example? So it is a problem number 8.41. So assume that the sample variance to be of continuous measurements. You have to find the probability that the random sample of 25 observations, so my small n is 25, from a normal population with variance, so your x is normally distributed and variance is 6, will have a sample variance greater than 9.1. Okay, so let us try to solve this problem first. So you want to find what is the probability that s square is greater than 9.1. But we don't know what is the probability distribution for s square. So what we do is we multiply by n minus 1 on both sides and we divide by sigma square, right? That's what we did because this follows the chi-square distribution. So this is greater than, you multiply by n minus 1. Now what was your n? Since your n is 25, so n minus 1 is 24 into 9.1 upon variance is 6. So there is nothing but probability. What is this? This is nothing but our chi-square. So chi-square greater than this one, 6 ones are 6 fours are, so this is 36.4. So you want to find the probability that chi-square will take the value greater than 36.4. Okay, so now we are going to see the table for this, but ultimately if suppose this is the chi-square distribution, this is 36.4, I want to find the probability that the chi-square values are greater than 36.4. That means I want to find this area below the curve, which we denote by alpha. Okay, so for this I will need degree of freedom. We know that this is a chi-square distribution with n minus 1 degree of freedom, right? So degree of freedom is 24. So now let us go in the table for chi-square distribution. Our degree of freedom is 24 and we want to look chi-square to be 36.4. We want to find this alpha. Okay, so keep this much in mind. Now let's try to see the table. So here you can see this is a table for chi-square distribution. Now you can see what is this bottom, chi-square alpha. That means this is a chi-square value and the alpha means what? The area towards the right is alpha. Now in our case, how much alpha we want? We want to find this alpha. Okay, the probability that chi-square is greater than 36.4. So here if you see, the left hand side is a degree of freedom and these are the values of alpha. That means the area that is left towards the right. Okay, now I will look for the degree of freedom. I will look for 24 degree of freedom. Okay, so you can see here is a 24 degree of freedom. Can you see 36.4 anywhere? in this row you cannot see 36.4 anywhere. So what you do is you go on to the next page. There are two pages. You can see this is also chi-square distribution. So on this page also you go for n equal to n minus 1, which is 24 degree of freedom. Can you see? Can you look 36.4? Here you go. 36.4 is here. Column number first, second, third, fourth. In the fourth column. In the fourth column, what is alpha? 0.05. Sorry. 1, 2. So 24 means 36.4. Yeah. So column number fifth. So alpha is 0.05. So if you come back to your, let's go back to the whiteboard. So how much is alpha? So answer is the probability that chi-square will be greater than 36.4 for 24 degree of freedom is 0.05. So that means 5% of the area is covered here and 95% of the area or the data is covered here. Okay, so that is the answer for the first part. Now let us go for the B part. Now what does the B part says? You want to find the probability that S square sample variance will take the between 3.462 and 10.745. Okay, so you want to find probability that S square will take the value between 3.462 and 10.745. Again the same thing, you don't know the distribution for S square. So what you do, you multiply both sides by n minus 1 and divide by sigma square. So n minus 1 is how much? 24, correct? And your sigma square is 6. So when I divide, the division is 4. So ultimately I have to multiply by 4 this side. So when you multiply by 4, I get 13.848 less than chi-square less than 40.980. So like standard we do our Z distribution problems that we have seen earlier. So this is chi-square less than 40.98 minus chi-square less than 13.848. But if I want to use the table is given, the alpha values are given for the right side, not for the left side. So what I will do, I will do this as 1 minus probability of chi-square greater or equal 40.98 minus of 1 minus. So minus 1 plus probability of chi-square greater or equal 13.848, or you can say 13.848. So 1 and minus 1 goes away. So what is chi-square greater or equal 40.98? Okay, so coming to table, you can see the 24 degree of freedom is here and 42.98. Okay, so oh yeah, this is 42, my mistake. 42, so it's 42. So chi-square greater or equal 42.98. So for 24 degree of freedom, 42.98. If you see what is the alpha value over here, the alpha value over here is 0.02. So here it will be 0.02. And what about this? Next is what? 13.848. 13.848. Can you see 13.848 at the 24 degrees of freedom? It is not on this page, so we'll go to earlier page. On 24 degrees of freedom, 13.848 is here. So it is nothing but 0.95. So you do 0.95 minus 0.02. I think it was 0.02. So anyways, I told you how to find the value. So you find values of 2 alpha, just subtract, and that's what the answer is. Okay, so the ultimate aim of taking this example was, now you can see that whenever there's a question on sample variance, we do not know the distribution for sample variance. So what we do is we multiply by n minus 1 divided by sigma square, so that we get a chi-square distribution. And once we have a chi-square distribution, you can always use the table for chi-square. Okay, so I hope this is clear. Let's go for the next problem. So now 8.42, the question is, now the scores on a placement test given to college freshmen for past 5 years are approximately normally distributed with mean 74 and variance is 8. Would you still consider variance 8 to be the valid value of the variance if you are taking a random sample of 20 students, okay, whose variance is, who take the placement or obtain a variance of S square equal to 20. Okay, so that's what the question is. You want to see whether this value is valid or not. Okay, now see for chi-square distribution. Okay, so let's first do some calculation, then I will come to one important point. Okay, so S square is given to be 20. So again, I want to find probability. What I want to find probability that S square is taking the value 20. What is the probability? So you multiply by n minus 1 both side. So 20 sample is taking, so n minus 1. So 19 into 20. You divide by sigma square. Sigma square is 8, right? So this is probability of chi-square equal to 19 into 20 divided by 8. So if you do the calculation, you get 47.5. Okay, now question is how much is this probability? And what is the degree of freedom? Degree of freedom is 19. So now let's go to the table and let us try to see what values we are getting. Coming to table, if you observe, see for this 19 degree of freedom, you can see here carefully these 3 values or these 4 values. See, our chi-square is 47 point something. Even if you take 36.19, that means area towards the right is 0.01. So for even for 36.91, let me just draw on the graph, you will realize it. So even if I take here 36.91 value, my area towards the right is 0.01. That means only 1% of area data is here, whereas 99% of the data is lying here. Now I am looking for 47.5. So definitely here it will be less than whatever answer I will get. I'll get less than 0.01, right? Because this much area is 0.01. I want to look on the right of 47.5, so that will be still less than 0.01. That means I am outside the area of 99%. That means I'm outside the area of 0.99. Okay. Now in chi-square distribution, see when there is one nice paragraph which is given in the textbook. I will show you. Your question was whether the calculation is valid or invalid. Okay. So whenever there is such a question, whenever the data is going outside 95%, we always say that there is a error. Okay. And if the data is within 95%, we say okay, there is no error. Okay. So what I'm telling you is written over here. So in this section, when you go for a chi-square distribution, yeah, so just read this part. See, exactly 95% of the chi-square lies between this and this, right? Because for this area towards the right is 0.025, for this area towards the right is 0.975. So when you subtract 0.975 minus 0.025, you get 0.95. So 95% of the values lie here. A chi-square value falling to the right of this, okay, to the right of this is not likely to occur unless sigma square is very small. Similarly, chi-square value falling to the left of chi-square 0.95 is unlikely to occur, and it's occur only if sigma square is too large. In short, it is possible to have chi-square towards the left and the right side of it, but if this occur, it is probably that there is some error in the value of sigma square. Okay, so if anything is going beyond outside this 95%, okay, anything is going beyond this 95%, we say that there is a error in the value of sigma square. Okay, so here what was the question? The question was, is the sigma square a valid value or not? Okay, but as we have seen that our chi-square value is going beyond 95%, so the answer is, would you still consider this to be a valid value of variance? No, because the output is going beyond 99%. We want it within 95%. Okay, it will get more and more clear when we study test of hypothesis. But as of now, if there is something kind of question whether something is valid or not, always stick to 95%. If something is within 95%, you will say yes, the data is valid. If something is beyond 95%, you will say the data is invalid. Okay, now let's go for the last question. Show that variance of S square for random sample of size n from a normal population decreases as your n become large. Okay, so I want to show that the variance of S square decreases as my n becomes large. Okay, so let us try to solve this problem. So I want to find variance of S square. I want to show that this decreases as my n increases. Okay, but I know that my chi-square is what? It is n minus 1 into S square upon sigma square, right? So what is variance of n minus 1 S square upon sigma square? This is nothing but my 2 times the degree of freedom. If you recall chi-square distribution, if this notation I'm saying, this nu is the degree of freedom, or some author also uses n. If n is the degree of freedom, then its expectation is n or nu, and the variance is 2 nu. Okay, so here this is a chi-square distribution, so its variance is 2 times the degree of freedom, and the degree of freedom is n minus 1. But what is the property of variance? This is a constant, this is a constant. So by variance property, this is a square, so n minus 1 square upon sigma raised to 4 into variance of S square. This is equal to 2 into n minus 1. Right? If you recall, what is variance of ax? It is a square variance of x. So my a over here is n minus 1 upon sigma square. So that will come it out as a square. So what is variance of S square? It is nothing but 2 times sigma raised to 4 upon n minus 1. So as you can see, as my n will keep on increasing, this will increase, that means the fraction will decrease. So as n increases, my variance of S square decreases. Okay, so that's how one uses chi-square distribution very widely whenever you play with sample variance. Okay, so I hope all these concepts are clear and the examples are clear. If you have any doubt, you can ask me in the comment section. Thank you.